Any electrical contractor with an understanding of grounding would realize that one grounding electrode system is sufficient for any size building. Therefore, it is unlikely that additional grounding is the problem. However, it does not appear that the grounding electrode system has been properly installed. To achieve a proper ground, the grounding electrode must be driven into the ground at least 8 feet. Additionally, concrete should be poured around the rod to keep moisture in contact with the rod. Finally, an 8-foot long 2-inch wide copper strap should be used to connect the rod to the electrical panel. It is possible that the present grounding system is not adequate. A ground resistance test should be performed to determine if this is the case. The suggestion of installing a second ground is not only unnecessary, but it could actually be dangerous. Consult with a qualified electrician to inspect the electrical system and to make any necessary repairs. The purpose of a grounding system is to provide a path for electrical current to flow to the earth. This is important for safety because it helps to prevent electrical shocks. A properly installed grounding system will also help to protect electrical equipment from damage. There are 2 types of grounding systems: firstly, driven rod systems, and secondly, buried wire systems. Driven rod systems are typically used in residential applications, while buried wire systems are typically used in commercial applications. To install a driven rod grounding system, drive a copper rod into the ground at least 8 feet. The rod should be at least 5/8 inch in diameter. Once the rod is in place, connect it to the electrical panel with a 2-inch wide copper strap. To install a buried wire grounding system, bury a bare copper wire in a trench around the perimeter of the building. The wire should be at least 2 inches wide and it should be buried at least 12 inches deep. Once the wire is in place, connect it to the electrical panel with a 2-inch wide copper strap. The grounding system is a crucial part of any electrical installation, designed to protect people and equipment from electrical faults. Its primary function is to provide a low impedance path for fault current to flow back to the source, allowing protective devices like circuit breakers or fuses to quickly trip and interrupt the circuits. This minimizes the risk of electric shock and reduces the potential for fire. There are several key components to a grounding system, including the grounding electrode, the grounding electrode conductor, and the equipment grounding conductor. The grounding electrode is a conductive rod, plate, or other object that is buried in the earth and provides a direct connection to ground. Common types of grounding electrodes include copper rods, galvanized steel rods, and concrete encased electrodes. The grounding electrode conductor connects the grounding electrode to the electrical panel, providing a path for fault current to flow from the panel to ground. This conductor must be sized appropriately to handle the potential fault current. The equipment grounding conductor connects the non-current carrying metal parts of electrical equipment, such as enclosures and conduit, to the grounding system. This conductor provides a path for fault current to flow back to the source if a fault occurs within the equipment. When a fault occurs in an electrical system, current will flow through the equipment grounding conductor back to the source. This current will also flow through the grounding electrode conductor to the grounding electrode and into the earth. The low impedance of the grounding system allows a large amount of current to flow, which causes the protective device to trip and interrupt the circuit. Without a proper grounding system, fault current could flow through unintended paths, such as through a person who comes into contact with the faulty equipment. This could result in a serious or fatal electric shock. There are several factors to consider when designing and installing a grounding system. These factors include the type of soil, the size of the building, and the type of electrical equipment being used. The type of soil will affect the resistance of the grounding electrode. Sandy soil, for example, has a higher resistance than clay soil. The size of the building will affect the size of the grounding electrode conductor and the equipment grounding conductor. Larger buildings will require larger conductors. The type of electrical equipment being used will also affect the size of the grounding electrode conductor and the equipment grounding conductor. Equipment that is more likely to experience faults will require larger conductors. The National Electrical Code, or NEC, provides detailed requirements for grounding systems. These requirements are designed to ensure that grounding systems are installed safely and effectively. The NEC specifies the minimum size of grounding electrode conductors and equipment grounding conductors, as well as the types of grounding electrodes that are permitted. The NEC also requires that grounding systems be tested to ensure that they are functioning properly. Ground resistance testing is a common method for evaluating the effectiveness of a grounding system. This test measures the resistance between the grounding electrode and the earth. A low resistance indicates that the grounding system is functioning properly. A high resistance indicates that the grounding system is not functioning properly and may need to be repaired or replaced. Proper grounding is essential for electrical safety. By providing a low impedance path for fault current to flow back to the source, grounding systems help to prevent electric shock and reduce the potential for fire. When installing a grounding system, it's important to follow the requirements of the National Electrical Code and to ensure that the system is properly tested. Here are some additional details about grounding electrode systems. Grounding electrodes can be made of various materials, with copper and galvanized steel being the most common. Copper is an excellent conductor of electricity and is resistant to corrosion, making it a popular choice for grounding electrodes. Galvanized steel is less expensive than copper, but it is also more susceptible to corrosion. There are several types of grounding electrodes, including ground rods, ground plates, and concrete encased electrodes. Ground rods are the most common type of grounding electrode. They are typically made of copper or galvanized steel and are driven into the ground. Ground plates are large, flat pieces of metal that are buried in the ground. They are typically used in areas where it is difficult to drive a ground rod. Concrete encased electrodes, also known as grounds, are made of a length of rebar that is encased in concrete. They are typically used in new construction and are very effective at providing a low impedance ground path. The size and type of grounding electrode required will depend on the size of the electrical system and the soil conditions. The NEC provides detailed requirements for grounding electrode sizing. The grounding electrode conductor connects the grounding electrode to the electrical panel. This conductor must be sized appropriately to handle the potential fault current. The NEC provides detailed requirements for grounding electrode conductor sizing. The equipment grounding conductor connects the non-current carrying metal parts of electrical equipment to the grounding system. This conductor provides a path for fault current to flow back to the source if a fault occurs within the equipment. The NEC provides detailed requirements for equipment grounding conductor sizing. Grounding systems should be inspected regularly to ensure that they are functioning properly. The grounding electrode and grounding electrode conductor should be visually inspected for damage or corrosion. Ground resistance testing should be performed periodically to verify that the grounding system is providing a low impedance ground path. If the grounding system is not functioning properly, it should be repaired or replaced by a qualified electrician. In some cases, it may be necessary to install multiple grounding electrodes to achieve the required ground resistance. This is common in areas with high soil resistivity. The NEC permits the use of multiple grounding electrodes, but it also requires that they be bonded together to ensure that they are at the same potential. Bonding is the process of connecting two or more metal objects together electrically. This is typically done with a copper wire or strap. Bonding helps to equalize the potential between the bonded objects, which reduces the risk of electric shock. In addition to grounding electrodes, there are other types of grounding systems that can be used. These include isolated ground systems and sensitive electronic equipment grounding systems. Isolated ground systems are used to reduce electrical noise in sensitive electronic equipment. In an isolated ground system, the equipment grounding conductor is isolated from the building's main grounding system. This prevents noise from the building's grounding system from interfering with the operation of the sensitive electronic equipment. Sensitive electronic equipment grounding systems are used to provide a very low impedance ground path for sensitive electronic equipment. These systems typically use a dedicated grounding electrode and a dedicated grounding conductor. Proper grounding is essential for electrical safety and for the proper operation of electrical equipment. When installing or maintaining a grounding system, it is important to follow the requirements of the National Electrical Code and to consult with a qualified electrician. Remember that one grounding electrode system is generally sufficient for a building. Ensure the grounding electrode is driven at least 8 feet into the ground and consider using concrete around the rod to maintain moisture contact. A 2-inch wide copper strap should connect the rod to the electrical panel. Conduct a ground resistance test to assess the system's adequacy. Installing an unnecessary second ground could be dangerous. Always consult a qualified electrician for inspections and repairs to maintain a safe and effective electrical system. The information provided is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for any electrical work or concerns. Furthermore, it's critical to understand that local electrical codes and regulations may vary. Always adhere to the specific requirements of the local authorities having jurisdiction, which may differ from the National Electrical Code. Some regions have unique geological conditions or historical infrastructure that necessitate specific grounding practices. Consulting with local experts ensures compliance with all applicable codes and best practices for electrical safety in the area. In addition to the physical components of a grounding system, proper documentation and record keeping are essential. Maintain accurate records of the grounding system's design, installation, and any subsequent modifications or repairs. This documentation should include details such as the type and size of grounding electrodes, the routing and sizing of grounding conductors, and the results of ground resistance tests. Proper documentation can be invaluable for troubleshooting electrical issues, verifying compliance with codes, and ensuring the long-term integrity of the grounding system. Moreover, regular training for personnel who work with or maintain electrical systems is crucial. Training should cover the principles of grounding, the identification of grounding components, and the procedures for inspecting and testing grounding systems. Properly trained personnel can recognize potential problems early and take appropriate action to prevent electrical hazards. Finally, it's important to emphasize the importance of using only approved and listed electrical equipment and materials. Ensure that all grounding components such as grounding electrodes, conductors, and connectors are certified by a recognized testing laboratory such as Underwriters Laboratories or Intertech. Using approved equipment provides assurance that the components meet established safety standards and are suitable for their intended purpose. Substandard or counterfeit electrical equipment can pose a significant risk of electrical failure, fire, and electric shock. By adhering to these guidelines and working with qualified professionals, it's possible to ensure the safety and reliability of electrical systems through effective grounding practices.